Jai Hind. My name is Vivek Agarwal. I'm the Assistant Professor in the Department of Computer Science and Engineering and Ajay Kumar Garg Engineering College. So, today we are going to discuss the linear regression and the logistic regression in machine learning. So, it is, if we talk about the regression, these are the two most journal and the most common regression techniques well known in the machine learning as well as widely used in the machine learning. Apart them, there are various other regression thing also, but today we are going to focus on the linear regression and the logistic regression. Okay, so in the previous lecture already we had discussed a brief introduction about the regression, what is the regression and how it is differ from the classification problem. So let us revise the things again. So regression is basically to just find out the continuous numerical value, just to predict to find out from the given data set or given data example, or I must say for predicting a continuous value. Like if we are going to predict anything using the machine learning technique, we can predict a predefined class. Like we had a set of data which are categorized into various class, maybe like we had supplied a list of a set of images to the model for learning purpose, and all these images are either classified for the elephant or the lion. So for any new query, we can classify the problem into either that given query is belonging to the lion or belonging to the elephant. So that is classification problem. But in regression, we are more concerned about to find out the values. For example, if we need to predict the the weather, the weather for tomorrow, the weather forecasting, we can keep it the scenario. So in the case of classification, we need to identify like the temperature would be high, low, medium, something like that. But in the case of regression, we need to identify or predict the values, like it could be 29 degrees centigrade, it may be 42 degrees centigrade. Yes, so we need to identify that particular numerical value. So in the case of regression problems, we need to just predict or identify these continuous numerical values out of the model which already has been learned from the given example set or the data set. So, if we are talking about the prediction or the supervised machine learning, it's the part of supervised machine learning. Already we had gone through the supervised and unsupervised learning, semi-supervised learning. So, I'm not going to repeat again and again, but the point is it is a kind of a supervised learning algorithm. In the case of supervised algorithm, there used to be two type of the features, or we can call them, we can say like the all features given in the data set can be divided into two parts: dependent variables and the independent variables. The dependent variables is called as the target, or we can say the outcome feature, which we need to predict. In the case of given data set, we can call them, these are the outcomes on which basis we are going to make learning for our model. And in the case of prediction, we need to identify the value of this outcome feature. And these are the independent variables features. All other than the outcome features can be considered as the independent features or the input features which are behaving as an input for the given problem to identify the outcome of the problem. So, in case of machine learning, we can divide the regression machine learning into various categories. First is linear regression, polynomial regression, ridge and lasso regression, support vector regression, decision trees regression, random forest regression, and several are also there. These are the commonly known, or I must say the commonly frequently used in the machine learning. So, the concept of the linear regression is something like if uh, if we have some input features and if we can map these input feature into a feature vector, or we can call it feature space. So just let assume it is a feature space, a 2D feature space, which is good for displaying a particular feature, the data points on the basis of a particular feature value. So if there are several data example in data set which are belonging to particular classes, so we can show these point using two notations. A particular class 1 data points are shown by the cross and another class data points are shown using the circles. So, if we are able to separate them using a linear line, or we can call them if the given data set is linearly separable, or we can call it in the case of a mathematical model or the geometrical reference model, we can call them if we can separate these data points through a linear line, then we can apply the linear regression there. But if we are not able to have a have a straight line between these two type of the data points, then linear regression cannot be applied there. So for that, we are having some other kind of the regression techniques. In the case of polynomial regression, it assumes like all the data points are can be separated using this polynomial. Like this is the reason for a one class data points, and this is the reason for another class data point. So this is the basic concept behind the choosing a different regression techniques. Likewise, the support vector regression, it works on the model of SVM, which is quite very popular for the classification problem, and many times before already I have repeated the same statement. If any algorithm which is capable for to classify the, or I must say that that is widely used for the classification, for solving the classification problem, that can be used for the regression problem as well. But just what we will have to do, we just need to make some we need to add some more a little trick with the model, and my classification model can do the regression thing also. So if we are going to use SVM as an classification which is widely used for the classification problem for regression thing, then the support vector regression, it utilizes the concept of plane rather than we are talking about a straight line. We talk about a plane. If we can distinguish two classes or two different type of data points using a plane, then the SVM can be applied. Decision tree, it uses the tree like structure for doing the things. Random forest is kind of an ensemble method which integrate various multiple decision trees to make the prediction for calculating the expected value for making the regression on the given problem. So it is an ensemble technique. In future classes or in future lecture, I will going to discuss about the ensemble methods as well. So if we talk about the main application areas of the regression, yes, predicting price, what I said earlier, like where we need to identify a numerical value, a continuous numerical value we need to predict. Wherever we need to identify or predict or make a decision in the form of continuous numerical value, we can apply the regression. So predicting price, you can predict the price of the assets of anything, any product, any asset, etc., on the basis of the last trends, the past trends of the same commodity. Like the prices of the gold can be an example. The prices of the property can be an example. The prices of the appliances can be an example, etc. Forecasting trends. This is for forecasting the trends of the sales or any kind of any kind of the event which is having past data with us, historical data. We can forecast the expecting our the upcoming trends of the same event. Identifying the risk factors, we can identify the risk factor as well basis on the basis of the past experience data. We can utilize the same thing for the medical purpose. We can utilize the same thing for the risk calculation in the industries. We can do the things for identify the direct and indirect risk factors associated with the projects and project management projects as well, project management applications. So regression is very useful in such kind of calculations. Making decision, it could be used to recommend which stock to buy, Yes, to analyze which stock is going to scale up the price, which or which stock is going to downfall for degrading the price. So on that basis, we can make decision which stock we must consider for buying or which stock we must consider for the selling purpose. So these are the main application area of the regression, but we are not limited to these areas only. We can apply the regression anywhere in any problem solution where we need to find out outcome in the form of numerical data or continuous numerical data. So advantages of the regression is it is easy to understand and interpret and implement. Yes, as you said, we just need to plot the data points in the feature space and just apply the regression thing. Quite very easy to understand, a pure geometrical method. Robust for the outliers. Yes, if your data set is having some outliers, then it can handle these outliers because we are plotting each and every data points in the feature space. So if there is any outlier, that would be too far from the other data points, so we can handle, or we can eliminate these outliers. So the regression method can handle easily with the outliers, can handle both linear relationship, positive and negative. Is it? Yes, the relation, it focuses on the linear relationships only. It doesn't matter it is positive or the negative. Disadvantage, if we need to just list out a few disadvantages, then first could be the assume linearity. Yes, because the basic funda of the regression is based on the this linearly. It by default is assumes that data is linearly separable. The basic, the line could be the straight line or maybe some polynomial, but it based on the linear relationship of the data. So sometimes in few application it got the limitation of the model. Sensitive to the situation where two or more independent variables are highly correlated with each other, it has the multicollinearity. Yes, this is again a challenge with the regression thing. If there are various input feature which are having the same kind of the characteristics or properties in terms of the outcome. In the next slide, we are going to discuss it in the detail. So you would be having a good idea about the multicollinearity as well. And third case could be the third disadvantage could be the may not be suitable for highly complex relationship. If your data set is quite very complex, or your problem is too complex, which is based on various input features, then it may not be suitable for identifying the regression, identify the regression values. So we can avoid it. In these cases, we can utilize some other available algorithms for these purposes. So in the previous slide, we were talking about the multicollinearity. This is something like this is we can understand using an example, like there is a data set which is having three input variable x1, x2 and x3, and this is the y, this is the outcome feature, or we can call it the dependent feature. So the value, the outcome of y is dependent on x1, x2, x3. This is the y which is the outcome. This is a, we can consider it like a set. If this is a set and its value are depending on x1, x2, x3, but these x1, x2, x3 have no correlation with each other. So this is a case of no collinearity, means there is no correlation among the x1, x2 and x3. But in this case, we can see the y, the set y is sharing the properties of x1, x2, x3, means it is dependent on x1, x2, x3, as well as these x1, x2, x3s are also sharing their common properties, or we can say they are having some correlation as well with them, within them. So this is the case of moderate correlation among the input features. And the third case, you can see the x1 and x2 are overlapping to each other, more in approx 90% they are overlapping to each other. So y is dependent on x1, x2, x3, but x1 and x2 are highly correlated to each other. So kind of the correlation make the influence on the outcome as well. Sometimes regression problem got confused to which particular x1 or x2 to focus more for making the decision for the regression or the outcome of the y, the value of the y. So this can affect the regression. So now come to the main topic, that is linear regression. As I discussed earlier, this is a pure or simple regression model which is based on finding the linearity among the given data points. The idea is, whenever we are having a data set, first of all we need to plot them. We need to plot them in a feature space. If we talk about the feature space is something like it may be 2D, maybe 3D, maybe 5D. It will depend on the number of input features. If there are 5 input features, then that space must be 5D. If the input features are 2 input features, then it must be a 3D model, because one dimension is always would be your dependent variable for which you are going to plot the data points, and other dimension could be your independent variables or the input features in the given data set. So if there are total 5 input features, then your dimension your feature space would be of 6 dimensions. So generally we cannot plot such kind of the uh, you know uh, uh, plots, but we can break down them in 2D or 3D models. Then we can summarize the things. For the better understanding, we are now considering like we are having a single input variables and a single input variable, and one is outcome variable. So we need to just plot the data points. We need to plot the data points in the feature space. So on the basis of the value of this given independent variables, we are going to plot these various data points. Now the whole idea is to identify a line which is capable to separate two different type of data points. Like there are various data points which are having a different characteristics, and if we talk about the classes, they can be classified into several classes, or for better understanding, we are considering them like we can segregate them into two classes. So we must be able to segregate these data points using a straight line. So this line is called the regression line, as well as is called as the best fit straight line. So the idea of the linear regression or the simple regression is to find a straight line. In the case of polynomial regression, this line could be in form of some polynomial. Yes. So this is the difference. So if we are having a line, then we need to predict the new value. For that, if any new point arrives in the feature space, as well as the new data point arrives in the feature space, we plot them into the feature space, and we need to identify the distance from this best fit line, and on the basis of that value we can we can make the regression in the form of continuous value, like what could be the outcome of basis of this new provided input data point. The same thing can be understood using this diagram as well. Here we are having the different data points which are belonging to different class, which are distinguished using different color. It is of different kind, another kind, and another kind. There are total 3 types of the data input points there, and for segregation we are having a straight line. So whenever a new point, suppose a new point plotted here, we need to calculate the distance of this data point from the best fit line, and on that basis we can find out the expected value of this. So the same thing already we had discussed are written there. Now the main point is to understand like it works on a linear line, a straight line, and the formula for the straight line already we know, y is equal to ax plus c, where a used to be the slope value and c used to be the value from where the y axis is going to be started. In the same way we can understand in the case of simple linear regression, we can have a equation in this way, where a is again the same y-intercept from where we are considering the y-axis is going to be started. B is again the same the slope variable, and this is the u, a new thing. This can be understood something like this. If this line, maybe a few cases when this straight line is making some errors for making some regression for identifying or for predicting the value. So we can consider that error rate using this variable u. So we can put that value as well as for finding out the data point for the the value of the y, outcome y. This is for the simple linear regression when there is only one single input feature as we shown in the previous slide. But if we are having multiple input features in my data set, then we must be repeating the same procedure again and again and making their summation. So simply that would be the sum of this, sum of b of x. So a would be the again the same ones and u would be the ones, and this is the summation part of for all the features. Yes. And the third type could be your multivariate linear regression, where we can have the multiple output variables. Like generally we need to calculate just the temperature. What would be the temperature of for just consider an example. We need to identify, we need to forecast the tomorrow weather. Then if we are going to calculate or predicting the only the temperature, what could be the temperature, average temperature, then that is a single variable outcome. But if we are talking about the minimum temperature and the maximum temperature, then we are going to predicting two output variables or two outcomes, the minimum temperature and the maximum temperature. Then that would be a case of multivariate linear regression. So if we list out their advantages and disadvantages, advantage is very simple because the model is very geometrically, we can explain, we can understood very geometrically. And the disadvantage, outlier can have huge effect on the regression. Yes, it can handle up to a normal degree, it can handle the outliers, but if the outliers, number of outliers are very are high in the given data set, then yes, it is going to affect the performance of the regression. And the second point could be when you know the relationship between the independent dependent variable have a linear relationship. Yes, again, if your data set is having a linearity, or I must say that if the whole data set is linearly separable, then only then this algorithm can be applicable. Otherwise, it is not be applicable. And one other thing, if we are going to, if there are some, you know, if we are going to apply some technique for making the linearly separable data set, given nonlinear data set into a linear data set, then we are going to make some means. We need to calculate some means, and we are going to replace various values with the means. So on that basis, if we are getting a straight line, we are going to regression. Again, it will degrade the performance of the algorithm. Third is, it is susceptible to the overfitting, but it can be avoided using some dimensionality reduction technique. Yes, overfitting can be, in general cases, the overfitting can be an issue in case of linear regression, and we can handle this using the dimensionality reduction, or we can call it like by reducing the number of input feature. But if we are going to reduce the input feature, then again it can degrade the performance of the regression or the performance of the model. So this was the all about the linear regression. Now come to the logistic regression. As we seen, the linear regression was typically working for the regression thing, for making some regression outcomes, for making the regression predictions. But logistic, a special case of the regression by default, which is used for the classification problems. But using some tricks, again we can use it for the pure regression thing as well, but by default it is designed for the classification problems. Now the point is why it is called regression, and if it is regression, why it is being used for the classification problem. Yes, the basic idea of the algorithm is based on the regression, as we seen in the previous linear regression. The idea is based on the same, but it is predicting in the form of classes. If your given data set is divided into various classes, generally there used to be a binary case, binary classification case. It is very helpful for the binary classification. If we are having more than two classes, then it may be some limitations for calculating the classification in multiple multiple outcome classes. So this is based on the regression, but being used for the classification problem, as it is designed to make the prediction in the form of the predefined classes. So what is the difference between linear and logistic apart from its application? The difference is this curve. You can see this curve. This is kind of the S-shaped type curve, or called as the sigmoid function as well. This is called the sigmoid function or the sigmoid curve as well, and the S curve. So in the case of linear regression, we were trying to make a linear line, a linear best fit line, which is separating various data points. But here we need to draw, or we need to identify a a S-shaped line which is separating the data points. This is the general geometrically difference we can see. And if we talk about the how to calculate the things, the way is same, but it is going to be make the outcome in the form of classes. So the idea is we need to identify again one more thing, that is the threshold value. If this is your curve, we need to identify a threshold value from where the below, from that point, that would be belonging to a particular class, and above that threshold point, all the given data points or predicting data points must lie to a different class, and that class can have a specific value, a continuous value, or maybe a labeled class. This may be anything. So the idea is very clear. The pure classification can be used for the pure classification problem, but you can see we can predict the numerical values as well on the basis of this line. So can be used for the regression as well, but by default designed for making the prediction in the form of 0 and 1. Like if the given query is lying between this threshold, then the outcome would be 0. Whatever the outcome, y is equal to 0 0.335, 0 0.4, whatsoever, that will be final outcome would be 0. And if the outcome of the regression is above 0.5, it may be 0.51, it may be 0.6, 0.7, 0.8, etc., etc. That would be always resulting final outcome as 1. Okay. So if we talk about the types of logistic regression, there are the three types of the logistic regression: binomial, multinomial, ordinal. In binomial, a binary, only two classes, two types of the outcome could be there, 0 or 1. In multinomial, there could be the various classes like cat, dog, sheep, or low, high, medium, etc., etc. If we talk about the ordinal, it is a special case of the multinomial where we are having an ordinal, like we are having the outcome classes in an order, in a specified order, like low, medium, high. Yes. So this is all about the types of this. If we talk about the advantages, these are the advantages: simplicity and easy interpretation. This is computationally efficient, probability outputs, less prone to overfitting compared to the linear regression, and work well with the linearly separable data. Yes, if your data is linearly separable, then it works very fine, but can handle the if it is not 100% linearly separable, but near about linearly separable, then it can also be applicable. Handle multi-collinearity, or we can say the multi correlation. If there are multi correlation between the input features, it can handle. Effective on the small data set, extensible for multi-class classification. As we talk about, if there are not only binary 0 1, if we are having multiple classes, then this algorithm can handle such cases also. Quick to train, very quick, it took a very less amount of time to get the training, the model get trained. versatile with feature engineering. Yes, you can optimize the feature. You can work with the feature engineering things like you can reduce number of input feature. You can change their values. You can replace their values. You can scale these values. So these are the main advantages of the logistic regression. If we talk about the disadvantages, lie in the within the same class of the linear regression, like assume linearity, mostly based on the linear relationship of the data, sensitive to the outliers, same as it was in the case of linear regression, limited to binary classification. Yes, basically designed for the binary classification, but can be extended for the multi-class classification as well using some tricks, additional tricks. Poor performance on nonlinear data, as I said, we can work on a little amount of non-linear data as well, but poor performance we are going to achieve using this algorithm. Requires large sample diet for a stable result. Yes, if your data set is too small, then the outcome would not be very satisfactory. And multi-correlationship issues, yes, it is again up to a small degree, or we can say a limited degree, it can handle the correlation of the input feature. But if the degree of the correlation of input feature is very high, then this could be an issue with this algo as well. Limited by the data quality. Yes, if the data quality is not good, the given experience, past experience data, then it is not going to provide a good outcomes. Does not capture complex interactions. Yes, issue with the complex things. So this was all about the linear regression and the logistics regression. In the next class, we are going to discuss any new topic. So thank you.